Hello everyone, my name is Yuxiang Guo, a fourth-year PhD from Johns Hopkins University. Today, I will introduce our work, Distillation-guided representation learning for unconstrained gait recognition. This work is cooperated with Siyuan, Ram, Peng, and advised by Professor Rama Chellappa and Professor Peng. At the beginning, let's review the method for the person recognition. The first one definitely be the face recognition, which is widely used in our daily life, including unlocking the phone. But how about this case? The face is undetectable, let alone do the recognition. Then the body recognition may come. It compares the appearance in the gallery and the probe of the human body. But how about this case? Due to the long distance, the person size is really small and there is an atmosphere turbulence. And also the person changes the clothes that make the appearance-based method is less reliable. Therefore, we transfer to the temporal-based method, namely the gait recognition. The gait recognition has an assumption that different people have a different walking pattern. Therefore, we could use this kind of pattern to recognize a person. For the gait recognition, most of the pipeline is like this. It's input with original video and do the segmentation, get the silhouette, and then it normalizes the size into the same 164 times 64. And then this normalized one goes through the backbone as a representation. This representation will be used to calculate the loss for training to optimize the backbone. And for the inference, it will be used to represent the clip. We found that for previous method, there are several problems. So first one is gait present always. That may be not true, since in the video, a person may just walking and then stop. So the people do not always walk in the sequence. And also, occlusion leads to the appearance-based difference. We could see the second one. Only the partial body are shown here, but due to the size normalization, the size will be expanded. Therefore, the temporal consistency between frame will not hold. Another problem is actually we miss a lot of information during the training. Like the viewpoint information is helpful, but this information is missed. For like this example, for 0 and 180 degree, one sequence is the person go to you, another one is go away from you. But based on the normalization clip, they look like the same. And also RGB contains rich information, but we get rid of it. Like sometimes the arm is occluded by the body cell itself. For the silhouette, we cannot see it, but for RGB, we will see how the arms move. So for the first problem, we try to refer the face recognition. We found that the faces are first detected and then do the recognition. Therefore, whether we could introduce a gait detector, there is one challenge that for the gait is a temporal information, so it's mostly represented by the volume, which will spend a lot of computation to extract the feature and deal with it. So it's challenged to introduce a lightweighted model to accurately determine the gait. Therefore, we first find a good representation for it. We use a double helical signature, which describes the motion of the knee. In order to get the knee's position, normalize the silhouette provide a good hint. It's about 1/4 of the height, which is the knee's position. Therefore, we could use this 2D frame to describe the motion. We consider the 4 conditions. For the incomplete body, the supposed knee height will be the side. Therefore, the the size will be much wider and thicker. And yeah, if there is walking, we will see the pattern. If not, there will be just a straight line. This appearance is really obvious, so we use a really lightweight, like 5-layer model to classify will be enough and get a high accuracy. Additionally, we also want to know where the gate start and where it end. Therefore, we split the whole sequence into multiple various length windows and do the gate recognition detection separately. That is the initial guess for the first line. And then we use non-maximum suppression, which is widely used in the detection to reduce the false positive estimation. After that, we merge the different bounding box if the inner distance is smaller than the threshold. Therefore, we could know where the gate start and where it end. Additionally, for the missing information, the viewpoint we found is eliminated during the site normalization. Therefore, during this process, we not only get the normalized silhouette, we also record the height ratio. In order to show the height ratio's effectiveness to represent the viewpoint, we do the test on the KCB dataset. Since it provides the viewpoint information, we found that like 90 degrees, the ratio will be a kind of constant. And for the symmetric angle, it will also show symmetric pattern for them. Therefore, we could say that the height ratio pattern could be served as the hint for the viewpoint angle. And this is a good descriptor since comparing to discrete one, like directly estimate the viewpoint angle. Since for our case, so relatively viewpoint is always changed. It's not a constant. Therefore, using a continuous pattern to represent it will be more beneficial. Another direction is using the RGB to distill to the silhouette feature. What we did is we use knowledge distillation method to get the knowledge from the RGB to get a better feature extraction for the silhouette branch. Therefore, our total pipeline is like this. We name it the gate detection and recognition gator. So at the beginning, it uses get a double helical signature, go through the gate detector to determine whether it is a qualified gate or not. If not, we will go through the body recognition. If it is it's a periodic movement with a complete body, we will use it for the gate recognition. For gate recognition model, it has a two-stage. During the training, it will use the racial attention or the viewpoint information and the RGB branch. The RGB branch will get the not inner feature to distill to the silhouette. Therefore, the silhouette branch will get the ability to get some hint about the RGB feature and get some discriminative feature from the RGB that the silhouette may not could generate by itself. And during the test, we will follow the most gate recognition method, only use the silhouette one, but this backbone has benefit from the RGB feature extraction. Therefore, it has ability to get some hint like where the arm is. In order to show the effectiveness of our model, we do the test on the broader data set. It's a really challenging data set. It contains the different condition. It compares the galleries from the indoor case and test Prabhakar for outdoor with a different closed setting. And for outdoor, it also have multiple walking conditions, the structural walking, the stand and random walking, and also consider various distance like 100, 400, 500 meter, and also the viewing point, the UAV. These are our performance on the broad data set. We test on the 4 backbones, gate set, gate part, gate GL, and gate base. We found that for the GAR, it's a model without help of the gate detector. And we found that with the help of the RGB information and the viewpoint, the performance will increase for all of them. And when we further introduce the gate detector, it will further improve and almost doubled compared to the baseline. As for the gate detection, we use the confusion matrix to show its performance, and our accuracy is over 90%. And also, I show some visualization here, and we found our gate detector to accurately tell where the gate start, where it end. And this work is supported by the artificial intelligence for engineer and medicine lab. And thanks for my advisor, Professor Rama Chellappa, to support this project. And also thanks for other colleagues to help me to get some advice and help me edit this paper. And also this research is supported by IAPA. Thanks for listening.